Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management, right? So within this module, we're trying to understand that how does the operating system manage the hardware resource, that is the CPU, the most fundamental piece of hardware in the computer system, right? How does the operating system manage it via this abstraction of a process? So this is what we are trying to cover in this module. And within the second module, currently we are on the last topic, that is the CPU scheduling policy, right? So within this topic, we are trying to cover different CPU scheduling policies or algorithms, which the scheduler uses to pick the next process that has to be run on the CPU, right? So as we know, the overall problem that we're trying to solve is that we want to run as many processes, like we want to run several processes on a limited number of CPUs. And for that, we need to share the CPU time among all the processes. And that is where CPU scheduling comes into the picture, right? And within the CPU scheduling, a very important question is that which process should the scheduler pick to run next on the CPU? And this choice can be very important, right? And so that is why we are trying to study the different policies. So in this video, we'll start with the first policy, the most simple one, that is first come, first serve, right? So let's study how this, what is this policy about and how does this work in this video. So let us start with the definition, or basically how does the first come, first serve algorithm work? So basically first come, first serve or FCFS scheduling is a non-preemptive CPU scheduling algorithm where processes are executed in the order they arrive, just like a queue. So it's very simple algorithm. It basically, the name is self-explanatory, first come, first serve, right? So it works by prioritizing process in the order that they arrive into the computer system. So process which arrive early will be favored, and process which arrive later will be like serviced after the process which have arrived before them have been allowed to run on the CPU. It works like a queue, right? So a very important part in this definition is that it is a non-preemptive algorithm, right? Which means that once the processor has scheduled the CPU to a process, right, then that process will run for as long as it wants to. The CPU will not be taken away from that running process, right? This is the definition of a non-preemptive algorithm. So in contrast, if there is an algorithm which is preemptive, then at any point in time, the scheduler or the operating system has the liberty to take away the control of the CPU from the currently running process. But that is not the case in the non-preemptive. Once the process starts running, only when it voluntarily gives up the control of the CPU, let's say it comes to a halt, that is, it terminates or it blocks or whatever reason, the process has to give up the control on its own. Then only the control of the CPU will be given to some other process. So this is the basic idea behind first come, first serve or FCFS scheduling. It's a non-preemptive policy, right? And it prioritizes process in the order that they arrive into the computer system, right? Very simple. Let's now understand this with the help of some real life examples also. So this first come, first serve policy is not just something that we see in computer systems, right? It is a very generic policy taken from real world, which basically is based on this principle that if people or if entities are early, then they should be favored. So whenever it comes to giving some kind of service, then whoever has arrived first, they will be served first, right? So some real life example is that let's take the example of an ATM. When you go to an ATM machine, right, then to withdraw the cash, then you have to queue up, right? So another example is that of a grocery store, there is a cash counter and there is a single person, let's say. Then you stand in a queue, and one by one the cash counter or the people at the sales process the, or like process your billing. So you have to stand in the queue, you have to wait for your turn. One by one, each of the person will get a chance to get their billing done. So this is the first come, first serve policy. The one who comes first will be given the chance first. The one who is in the last in the queue will be given the chance to get their billing done in the last, right? Similarly, another example is that of when you're traveling, you go to the airport and you're like doing the check-in. There, you in the luggage queue also, in the check-in queue also, you have to stand in a queue. The people who are in the first, who are earlier, get to drop their luggage or do the check-in earlier. So it's a fairly simple, fairly common policy, right, which we come across in our daily lives also. So the same principle or the same idea has been borrowed and applied to the to this problem of CPU scheduling. That is, given a bunch of processes, which process should we pick up? So the idea is simple: the one which arrives earlier should be favored, right? So let us now understand this algorithm with some examples, right? We have understood the basic idea. Now let's see some examples. So we'll start with a very simple example. In this case, there is a hypothetical computer system, let's say, and it has three processes, P1, P2, and P3, right? So the arrival times of these processes has been given. Let's say P1 arrives at 0, P2 arrives at 10, P3 arrives at 20. And I'm assuming that all of these processes have an equal burst time. Just to keep this example simple, all of these processes have a burst time of 30 units, or let's say 30 milliseconds, right? Which means that each of the process will spend the time that each of the process would spend executing their instructions on the CPU is 30 milliseconds, right? Then there are some note in the in the bottom. The first point is that the runtime of each job is known. So this is a very important point, or I would say a very important assumption that we should clarify. That in this example and in the further examples also that we'll see, uh, when we are discussing an example, we say, okay, this process has a burst time which is already known, which means that we already know how much time that it would take for that process to execute on the CPU, or we know beforehand that how much time that the process would occupy or run on the CPU. But this is a very strong assumption, right? This is not the case in real worlds. When you're using any kind of program, right? When you launch any kind of program, then it is not known beforehand. At least the computer does not know how long will you use that process, right? How long will that process run? It could end instantly or it could run for hours. So this is something which is an indeterministic problem. But for the sake of study of algorithms, like the easy algorithms, will assume that the runtime of each process is known. Slowly we'll relax this. There are algorithms, the algorithms that we use in the real computers do not need to know, or they cannot even actually know the runtime of the process beforehand. They work on certain ideas that does not require the knowledge of the burst time of the process at the starting. So but for the study, for the since we're starting the study, and for the simple algorithms, we'll assume that we already know the runtime of each job. But this is something which is a very strong assumption, and we should clarify, right? This is something that is not true in the real world. This is a hypothetical situation, right? The next point is that all jobs only use the CPU, that is, they do not perform IO. Right? To keep matters simple, I'm only assuming that each process is spending the time only executing instructions on the CPU. But that is obviously not the case. We have talked about this several times, that the life of a process follows a CPU IO burst cycle, right? So a process starts with a CPU execution, executes some instructions, then it issues a IO request. So it blocks for some while, it waits for some while. In that point, when it is waiting for the IO, it cannot even execute. So it is not in the ready state. Then it unblocks, executes instructions for some time, then again does IO, blocks. And in this way, it alternates between executing instructions on the CPU and being blocked for the IO to complete. But for the sake of study, we'll assume that the processes are simple. They do not have IO burst, they only have CPU burst. That is, they only execute instructions on the CPU and then they finish. This will allow us to keep the example simple and focus on the properties of the algorithms, right? So having made these assumptions clear, let us now apply the first come first serve policy to this simple example, right? So we'll make the Gantt chart just like for any scenario when we have a when you have a bunch of processes or a workload that we want to schedule on the CPU. We understand that via plotting the Gantt chart or drawing the CPU scheduling diagram. So let's do that. So we are going to use the first come first serve, and this is the Gantt chart, the timeline diagram. So here is the operating system. This is the scheduler which works with the ready queue. So it is very important, and we have already talked about this, that the scheduler will pick a process from the ready queue. Only those processes which are in the ready state are like valid candidates that can be selected to run on the CPU. If a process is in the waiting state, it is in the block state, then even if the scheduler gives the control of the CPU to such a process, then it won't be executing instructions. So all the choices, any choice that the scheduler makes happens from the ready queue, right? So we have three processes, and let's say process P1 arrives, right? So it arrives at t is equals to 0, right? And we have not yet scheduled process P1. It has just arrived. You can see it is now in the ready queue. It has not started running on the CPU yet. So at t is equals to 0, now the scheduler has to make a scheduling decision, right? At this point, there is only process P1, because process P2 will arrive at 10 milliseconds and process P3 will arrive at 20 milliseconds, right? So from 0 to 10, there is only one process in the system. So here there is as such no choice, right? The only process that is there in the system that will be selected to run on the CPU. So as such, whatever policy is being followed, when there is only one process, then there is as such no choice. So for the first 10 milliseconds, the scheduler allows process P1 to run on the CPU. At t is equals to 10, you can see that process P2 arrives in the system. And we know that all of these processes have the burst time is 30 milliseconds, right? So P1 has already executed for 10 milliseconds, 20 milliseconds are still left. And at t is equals to 10, process P2 arrives in the system. Now, what will happen? Will process P1 continue, or will the scheduler pick process P2 for execution? Because now there is a choice, right? There are two processes in the system. Until now, there was only one. But now, when process P2 has arrived, there is a choice. So, what should the scheduler do? So here is where we have to learn to apply how the policy works. There will be many policies that we will study forward, but the main idea behind learning a scheduling policy is to know what happens when new processes arrive, when are scheduling decisions made, and on what basis. So that will basically help you to draw the CPU scheduling diagram. So if you have a good idea of the policy, then only we will be able to make the or schedule the processes. So now, since this is a simple first come first serve policy, we know that the processes will be scheduled in the order that they arrive. So P1 had arrived earlier than P2. You can see the arrival time of P1 is 0 and the arrival time of P2 is 10. So obviously P1 will be favored. And most importantly, this is a non-preemptive scheduling policy, which means that once P1 has been allocated the CPU, it will continue execution unless it voluntarily gives up the control of the CPU. That is, either it terminates or it blocks. But since we are assuming that there is no IO, right? So it will never block, right? So that is why we simplified this scheduling problem. The processes only have burst time, that is, they only execute instructions on the CPU, they will not block. So this means that process P1 will give up the control of the CPU only when it terminates, right? So P2 has to wait. P2 is in the ready queue, so P2 has to wait. So P1 will continue execution, right? And at t is equals to 20, now the last process also arrives, that is P3, right? P3 also arrives in the system, and now we have three processes in the system. Again, we have to re-evaluate the situation, right? Whenever a new process arrives in the system, whichever policy you're following, whenever a new process arrives in the system, it is a it is equally an important candidate that we should consider. We are thinking from the perspective of the scheduler, right? So whenever a new process arrives, it could be the case that the new process is a better candidate, whatever goal we are trying to optimize for, right? So again, an important point that I had to clarify, this is first come first serve algorithm, and we said in the previous video that this is an algorithm that is applied on batch systems, right? We talked about batch systems in the previous video in detail. In short, the idea is that in a batch system, there are a bunch of jobs that are submitted and then they're executed without much user interference. So in a batch system, there is no user as such sitting in front of the terminal and demanding response time. So we talked about this in the previous video, that the goal of a batch system is to optimize for throughput, that is high throughput and low turnaround time, right? And we are concerned with having a low turnaround time, right? Throughput also, we assume that will only optimize basically for low turnaround time, right? To keep matters simple. So now the thing is, this is a batch system, right? And first come first serve policy is only for batch systems. And in batch systems, the criteria that we are optimizing for, so that is the most important thing. What is the criteria that we are optimizing for? We are optimizing for turnaround time. That is turnaround time. We also studied that it is the time that it takes for between a process arrives in the system to the time it completes. The entire duration that a process spends in the system, that is known as turnaround time, right? So turnaround time is basically the total duration that the process spends, or the life of the process in the system. We want to minimize turnaround time. We want to have process finishing quickly. They're arriving and finishing as soon as possible. This would be an ideal batch system, right? So let me summarize. We did a little bit of detour. So let me summarize that for you. This is a batch system. First come first serve policy is applicable for batch systems. Why? We'll see. Right. So in a batch system, we are optimizing for what goal? We are optimizing for low turnaround time. The lower the turnaround time, the better the system will be, right? There are a bunch of jobs. We do not care about the user, providing response time to the user, but we care about finishing the jobs as quickly as possible, right? So each job should spend minimum time in the system. That is what we want. In a batch system, in an ideal batch system, the process will finish quickly, right? So now whatever, so why are we talking about all of this? Because I was talking about that whenever a new process arrives in the system, then we have to re-evaluate the situation. Why are we re-evaluating the situation? Because we are optimizing for some goal. In this case, we are optimizing for throughput. Sorry, we are optimizing for turnaround time. So whenever there is a scheduling policy, it has a goal in mind. It has to optimize for a criteria. In this case, first come first serve, which is running on a batch system, its goal is to optimize for low turnaround time. It has to make a selection in such a way that the jobs finish quickly. Finishing the jobs quickly is the purpose of the scheduler. So coming back, now it was t is equals to 20 milliseconds, right? So at t is equals to 20, when process P3 arrives in the system, I said that it could be, so we have to reevaluate whether this P3 is a good candidate or not. And why we have to evaluate? Because we are optimizing for a criteria that is low turnaround time, right? So there are three processes in the system, P1, P2, and P3. The idea behind the scheduler is that it has to use the policy to make the optimal decision, right? So whether optimal or not, we do not know yet. We are following a policy. Whether it is optimal or not, that we will judge later on, right? So now we do not have to think much. We have a policy. We have a, like, the policy is based on a rule and we have to follow that rule, right? So the rule is that the process which has arrived earlier will be favored, and it is a non-preemptive scenario. So P1 will be continuing. It will be allowed to continue. We will not preempt the process P1. So P1 will continue. It will finish after 30 milliseconds. Then P2 will be allowed to execute because P2 arrived after P1 and before P3, right? So we are following the order. So it will be fairly simple. P2 will execute from 30 to 60 and P3 will execute from 60 to 90. You can see as the process finish, they go away from the ready queue, and when they terminate, their process control block is basically destroyed. The process is terminated. So this is the Gantt chart at t is equals to 90 when all of the processes have finished, right? So now let's see how does this policy perform, right? Coming back, this is a batch system. Our goal is to have a low turnaround time. We followed some kind of a policy. We followed the first come first serve policy. We do not know yet whether this is a good policy or not, right? We just said that, okay, we'll try to follow this policy because it is a fairly intuitive uh, rule that if a process is arriving early, it's a fair thing to allow it to run, right? Because in real life also we follow this policy a lot. So that is why we're trying this policy. Let's see how good this policy is. How do we judge that? So for that, we'll have to first of all calculate the turnaround time, which is the criteria that we are optimizing for. So since we know the completion time for all of the processes, we can calculate the turnaround time using the simple formula, that is completion time minus arrival time. So turnaround time, as I said, is the total time that any process spends in the system from arrival time up till completion time. So these are the turnaround times. For process P1 it is 30, for P2 it is 50, for P3 it is 70, right? So now these are the turnaround times. We can also calculate the waiting times. So waiting time we can calculate by subtracting the burst time from the turnaround time. We know that the turnaround time consists of two parts. One is the burst time, the other is the waiting time. During its entire lifetime, that is the turnaround time, the process could either be executing on the CPU or it could be waiting for the CPU. So in waiting state, we are actually, in this case, we are not actually blocked. We are just in a ready state and we are waiting for the CPU to be assigned. It is waiting because some other process is running on the CPU. All processes are equally ready. It's just that some process is running, so the process have to wait. So these are the waiting times. So let's calculate the average, right? We have two metrics now, turnaround time and waiting time. So waiting time is actually proportional to turnaround time because burst time is constant, right? So if you see this formula, waiting time and turnaround time. So since this is constant, if turnaround time is high, then that means waiting time is high, and vice versa, right? If waiting time is high, it means turnaround time is high or low, right? So now we calculate the average. The turnaround time, the average turnaround time is 50 and the average waiting time is 20. So what does this mean? In this hypothetical case, we had three processes. Each of them had a burst time of 30 and they're basically spending 50 milliseconds in the system. And on average, this is the lifetime of a process on average in this hypothetical situation, right? And they're waiting for 30 milliseconds, right? So we have a number, right? So how do you decide whether this policy is better or some other policy is better? You have to try different policies, right, on the same scenario, and whichever policy gives you the lowest turnaround time for a given workload. So when I say workload, I mean the bunch of process or the scenario on which we are applying the policy. So in this case, there were three processes, each having a burst time of 30, and there are certain arrival times, right? So to judge how good a policy is, you have to calculate the metric which you're trying to optimize, right? So in this case, on a batch system, when we are running the first come first serve algorithm on a batch system, the goal or the metric that we're trying to optimize is for turnaround time. The lower the turnaround time, the better. So we do have a number 50, and later on, when we study about other algorithms also, we can compare two algorithms. Since we only have one, so here we'll just talk about how first come first serve works. We are not going to talk whether it is optimal or not. That we'll get to know when we see other policies, and then we can compare the two policies. In this video, we are only interested in only learning how first come first serve works. Whether it is optimal or not, let me spell it out. It is not optimal, obviously. We'll study more optimal algorithms in later videos, and then we'll compare and see that for the same set of process, those algorithms will give a better turnaround time. So there are algorithms which can give us like better number than this 50, right? So this was one example just to give you an idea of how first come first serve works. We applied the algorithm simple, just in the order they arrived. We allowed each process to run on the CPU. We drew the Gantt chart. We calculated the turnaround times, the waiting times. So all of that we got familiar with of how you can use the first come first serve policy on a bunch of processes. So that was a fairly simple example, and in that example we did not really understand any pros or cons for first come first serve. So let's take another example, a more interesting example, and it will help you to see what are the problems with first come first serve policy. So the same, not the same example, similar example. We have three processes just like before, but here the burst times are a little bit interesting. You can see in the previous example, the burst time was 30 for all of the processes. Here what I have done is that for process P1, the burst time is high, that is 80. And for the other process, the burst time is quite low, that is 10, right? And these are the arrival times. And now let's apply the same policy, that is first come first serve, on this situation and see how does the policy fare, right? So again, we'll draw the Gantt chart, right? So let's start with process P1. It arrives at t is equals to 0, right? And as you can see, it is a very high burst time, that is 80, right? So it is in the ready queue. And at t is equals to 0, there is only one process in the system. And we already discussed that when there is only one process, there is no choice as such. That process will be the one that goes to execute on the CPU. The scheduler picks process P1, simple, right? And it executes it. And basically at t is equals to 10, I'm just showing here that the other process also arrive, P2 and P3. Both of them arrive at time instant 10, and they're fairly short process, right? So what will happen now? Now there are three processes in the system. We can reevaluate the situation, right? But reevaluation would not help because this is a non-preemptive policy, right? In a non-preemptive policy, once a process has been started, until it is not terminated, there is not much change. There is actually no change. So reevaluation does not matter. We are following first come first serve policy, which is a non-preemptive policy. Process P1 had arrived first. Only when it finishes, then we can even talk about other process. So first, let's finish process P1. P1 executes for 80 milliseconds, and at t is equals to 80, now we can reevaluate. Now we can think of other processes, right? Now P2 and P3, there are two processes in the system. Which one should be allowed to execute? We can see that both of them have arrived at the same time, right? So there can be a tiebreaker system. In this case, let's just assume that P2, since has a smaller process ID, the scheduler picks that process to run on the CPU, right? So since the arrival times are same, we cannot really compare based on arrival time. We have to do a tie breaking. So we just use the process ID. So P2, let's assume that process P2 is allowed to execute on the CPU. It executes for just 10 milliseconds. It's the short process compared to P1. And once P2 is done, we are left with P3. So P3 is the last one to go on the CPU. Again, P3 is also a short process and it finishes at t is equals to 100. Now let's see how does the first come first serve policy perform on such a workload, right? We tried to vary the workload. In the previous case, the workload was simple. All the processes had same burst time. But here the workload is kind of more skewed. Here process P1 has a high burst time and it arrived early, whereas the other process were shorter process, but they arrived later on. So let's calculate the turnaround time first of all. Again, we'll calculate the turnaround time by this simple formula, completion time minus arrival time. So for process P1, it is 80. For process P2, it is 80 again. And for process P3, it is 90. Let's also calculate the waiting time. So waiting time, like we did in the previous case, it can be calculated by removing or subtracting the burst time from the turnaround time. So these are the waiting times, right? Now let's calculate the average. You can see in this case, the average turnaround time is quite high, right? So what we are trying to say is that the processes on an average spend 83 milliseconds in the system, which is quite high, right? Now, if you compare this 83, why I'm saying this is a big number, if you see process P2 and process P3, their burst time is just 10. Basically, the amount of work that is to be done is only worth 10 milliseconds. But the overall time that they spend in the system to execute 10 milliseconds worth of instructions, it's 83 milliseconds. And as you can see, process P2 waits for 70 milliseconds, whereas process P3 waits for 80 milliseconds. You could obviously say that process P1 has a waiting time of 0, right? And turnaround time, which is exactly the same as completion time. So for process P1, the scenario is perfect. It did not have to wait, right? But for the shorter process, if you see, their waiting time is very high if you compare that to the burst time. For process P2, it was waiting for 70 milliseconds. That is 7 times more time it spent waiting than executing. For process P3, the situation is even worse. It is spending 80 milliseconds waiting and only 10 milliseconds of execution. So clearly, when the workload is somewhat different, right, then the turnaround time can be pretty bad if you're using first come first serve policy. So let's figure out what happened here. The problem with this workload is that here there is something which is known as a convoy effect. So what is a convoy effect? The convoy effect is basically when a long or a large process, a process with a very high burst time or comparatively higher burst time, arrives earlier than the other process, and basically after a long process there are several short processes arriving in the system. This workload like paired up with this policy, that is first come first serve. Now there is a problem. The first job, which is a large job, that will be fine, but all the other smaller jobs, they will have to wait for a long time. Since first come first serve is a non-preemptive policy, once that larger job has been started, that is once that job is allocated the CPU, it will occupy the CPU completely. Let's take there is a compute intensive process that runs for 3 hours. It could be, let's say it is processing some high quality video and it runs for 3 hours, and that process has been started in a system where first come first serve policy is there. And there are many small jobs that would only take 1 minute, let's say, and they arrived after this 3 hour job. So all of that 1 minute jobs will have to wait for this 3 hour job to complete, then only they will get their chance to execute. So you can clearly see when there is a skewed distribution, a distribution in such a way, when there's a long job arriving earlier than shorter jobs, then the performance of shorter jobs will suffer. And in this situation, the overall collection, when we judge a policy, we judge on the overall collection of jobs. So if you look at the overall collection of jobs, the turnaround time is high. On an average, processes are taking more time to complete, and this is something that we do not want, right? We are talking about batch systems here. The goal of the system is to have high throughput and low turnaround time. To be specific, we are considering low turnaround time, right? And you can see first come first serve can perform very poor if there is a skewed distribution of process, that is longer jobs arriving earlier and smaller jobs arriving later. And this particular problem is known as convoy effect, and this is the drawback of first come first serve. Although first come first serve is very simple, but it has this drawback, and this situation can occur like very commonly, right? It is very rare that processes have like a very fair simple distribution of burst times, like we in the example one. Here we assumed a very simple system with all processes having the same burst times, but obviously in real world processes have different amounts of computation times, and it could very well happen that a longer job can arrive, and in that case all the smaller jobs will suffer. So this is the main drawback of first come first serve. So let's also, before going to pros and cons, I was about to discuss pros and cons. Let's also talk a few more points about convoy effect. So convoy effect is something that we see in our daily lives also. Let's understand this from our daily lives, and we'll understand this in a better way. So let's say you're on the road, right? You're driving and there is some VIP caravan or a VIP convoy. VIP convoys, basically they have special clearances, maybe some politician or some security, for some security reason they have a big convoy. Basically there is some person and they are surrounded by a big convoy of security personnel, right? It could not just be security, anything. So there is a big convoy, and for that the whole traffic has to stop, right? So you are waiting, like you're just one car, right? Many people like you, they just have one car and they are waiting, and the time that they will take to cross the road, let's say, will be very small. But let's say there is a procession or a convoy of 30 cars that just comes, and by policy we have to wait because they have special clearance. So in that case you can see all of the, let's say there are 20 let's say there are 20 people waiting in the traffic. All the 20 people with the individual vehicles have to wait for that one big procession of 30 cars to pass. I'm just taking a hypothetical example. So you can see in those cases a big convoy can make other small cars wait, right? Others, not small, individual cars wait. So each of the 20 persons sitting in those individual cars, their turnaround time, like basically the time that they would have taken to cross the traffic, increases. They have to wait a lot because of this one big convoy, right? Another example is that on a train signal, when you see there is a signal that you cannot cross until the train crosses, right? There's a red signal and all of the individual vehicles have to wait. There could be again many people waiting on this road, but all of them have to wait for this one train to pass, and trains can take some time, like few minutes. They'll come and they'll go, and the signal will the time that will take to remove the signal can be a few minutes. So if you calculate the few minutes for every individual, then it could be a lot of time spent on waiting. But this happens in real life, right? So these are examples of convoy effect. Here there's a big convoy which is making the other smaller entities or smaller vehicles wait. And one last example is that of a grocery store. Let's say there is a grocery store, on the billing desk there is a, on the cash counter they are processing on first come first serve basis, right? So let's say there is a big trolley, a person with 2 3 trolleys full of grocery. He has just he's in the first in the line at the billing desk, and there are many people with just 1 or 2 items, and they could quickly get their billing done if they are allowed a chance. But there is a policy of first come first serve, and the first person in the queue or the first few people in the queue have big trolleys full of monthly groceries, right? So all of the people who are in the back with just 1 or 2 items have to wait a lot. If there was some way that we could have processed the smaller people with lesser number of items earlier than those with more number of items, then the overall turnaround time or the overall duration that people spend waiting on that billing desk line would be less. But there can be convoy effect, that is people with a huge more very large number of items in the trolley can be in the ahead of the line. They could be doing their monthly shopping, and due to them all of the people who have lesser number of items have to wait, right? So this is the convoy effect, where a large job or something which takes a long amount of time, due to that entity many small like many comparatively smaller jobs or entities have to wait. This is a convoy effect, right? So finally, let's discuss the pros and cons of this scheduling policy that we just studied. First come first serve, right? So the pros of first come first serve is that it's a very simple policy, right? It's very simple to understand. The jobs will be processed in the order of their arrival time. Very simple, fairly simple, and something that we come across our daily lives also. We saw several examples also, and it is very simple to implement. You can even also implement, right? So it's a scheduling algorithm which is very easy to implement as a developer, right? People who are writing the code, the later on algorithms and the algorithms that we use in the actual operating system are very complex, right? They are very complex to understand and implement. The real world scheduling algorithms I'm talking about, right? The That is what the advantage of first come first serve is, that it is easy to understand and easy to implement. The cons of first come first serve is that it has convoy effect, right? That we just discussed, which means that if there is a longer job arriving earlier than smaller jobs, then all of those smaller jobs, they might have very small burst times, but they will spend a long time in the system. Their turnaround times will be high, and on an average, the overall average turnaround time will become higher. So the system, the batch system for which this policy is being designed, it's basically the goal for which we are optimizing for, that is low turnaround time, is not met. That is why first come first serve is not optimal for batch systems. We want low turnaround time, but if we have a workload where there is a convoy effect, then that first come first serve performs very poorly. And finally, it is not good for interactive systems. As such, this is, we cannot say a drawback. First come first serve has its own application, right? It is meant to be used for batch systems. It is not designed to perform a good response time. As we saw in convoy effect, what will be the other metric that will be hurted? Response time. The smaller jobs, if you can see, the smaller jobs which arrive later on, the response is given to them at a very later point in time, right? So basically process p1 arrived at 0 and it started execution at 0, so response time to process p1 is good. But for process p2, it arrives at 10 and it starts at 80, so it spends 70 milliseconds waiting and only 10 seconds execution, so the response time is very poor for process p2. Similarly, for process P3, it is even bad. It has arrived at t is equals to 10 and started execution at t is equals to 90. So 80 milliseconds of waiting for process P3. Even the first response to come, process P3 has to wait for 80 milliseconds and process P2 has to wait for 70 milliseconds. And why? All of this is due to the convoy effect, right? So we can see that first come first serve gives a very poor response time, and we cannot apply it to systems which require interactive systems, right? In an interactive system, when we are running or interacting with multiple processes, it would be a very poor user experience if one process is responsive and the other processes are stuck, right? If one window is fine and the other windows are they're not showing any kind of response, that is something that we do not want when we are using when users are interacting with the computers directly. So for interactive systems, first come first serve is definitely not applicable. So this can only be applied in batch systems. In batch systems, we discussed in earlier videos that as such the user is not waiting in front of the terminal, so anyways response time is not the goal, so that is fine. So in batch systems, there are a bunch of jobs that are submitted and the system executes them one by one based on some policy optimizing for throughput and low turnaround time. So for batch systems, first come first serve can at least be used, right? But we saw that there are cases when it will perform badly, that is when there's a convoy effect, right? But for interactive systems, we should not even think about it, right? So this is the like pros and cons of first come first serve. So you could also say that first come first serve should not even be used for batch systems, because anyway if there is a convoy effect, then the turnaround time will be high, and even in an interactive system the response time will be poor. So let's now talk about interactive systems. For batch systems, at least we can say, okay, first come first serve, it's not a optimal algorithm, right? So this was just a starting point, since this is a very initial, very simple idea, right? These used to be used in early days of computing. Based on this understanding, we'll now try to refine our algorithms, come up with better algorithms. In the next few videos, we'll see algorithms which perform better than first come first serve, right? So this was about first come first serve policy for batch systems, where we are optimizing for low turnaround time. Simple policy, but has some drawbacks. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.